Another method of curve fitting is using methods of moments. In this procedure, one only has to draw equations to determine A and B. Learn about this method in numerical solutions to CE problems. In the method of moments, one has to solve preliminary equations of mu's and gammas in order to find a system of equations where A and B are included, thereby solving via substitution or elimination. They would be determined and eventually the equation will be drawn. In this method, a value for h should be strictly followed. H is the difference of the x values, which would mean that one condition for this procedure is to have the intervals of x be regular or equal. The first set of formulas or moments are from the true distribution of datasets, thus are known as population moments. The first moment, or mu1, is h multiplied by the summation of y's. The second moment, mu2, is h times the summation of x by y. And the third moment, mu3, is h multiplied by the summation of x squared times y. Mu is the population mean. Moments taken as mu are sample moments, and they are to be equated with the theoretical moments expressed as sigma. Theoretically, the first moment, sigma 1, is the integral of y dx, whereas the second moment, sigma 2, is solved as integral of xy dx. The third moment is computed as the integral of x squared y dx. As mentioned earlier, the sample moments would have to be equated with the theoretical moments. The sample moments are equated with the theoretical moments, thus the final equations used to establish the values of A and B are as follows. Let's show the procedure with an example considering the best fit line with y is equal to ax plus b format for the following set of data. H is then computed as 0.2 less 0.1 or 0.3 less 0.2, which would then yield 0.1. The first sample moment is determined using the formula, or that is h of 0.1 multiplied by the summation of all the values of y in the table. We compute mu1 as 0.6023. Take the second sample moment, mu2 as h multiplied by the summation of x by y. By placing all the values of x multiplied by y from the table, mu2 is then computed as 0.428907. After sample moments, solve for the theoretical moments, where the first moment comes from sigma 1, which is the integral of y dx, or the integral of f of x dx. F of x has a general formula of ax plus b, so taking the integral, we arrive at ax squared all over 2 plus bx, with the upper limit taken as 1.05 and the lower limit is computed as 0.05. With such limit values, expand the equation and plug the limits to x, which can give sigma 1 computed as 0.55a plus b. The second moment is also computed with a somewhat similar formula. For sigma 2, consider the integral of xy dx, or that would be x multiplied by ax plus b dx. Integrate the equation as ax cubed all over 3 plus bx squared all over 2. And by using the upper and lower limits, the equation is then expanded as a all over 3 times 1.05 cubed less 0.05 cubed plus b all over 2 times 1.05 squared minus 0.05 squared. Thus, sigma 2 is taken as 0.385833A plus 0.55B. With the two equations already known, you can either use elimination or substitution to come up with the variables. In this example, let's use substitution. So from equation 1, we can come up with b is equal to 0.6023 less 0.55a, which is then denoted as equation 1a. If we plug this value into equation 2, it would be 0.385833A plus 0.55 of B, which is taken as the quantity of 0.6023 minus 0.55A is equal to 0.428907, where 0.083333A is equal to 0.097642, and the value of A is solved as 1.1717. Then get back to equation 1 to solve for B, where we replace A with 1.1717 and B is then computed as negative 0.04214. With both a and b already known, the function of x can be stated as 1.1717x less 0.04214. Let's have another practice. Example 2 has 5 entries where we are required to find the best fit line with the format of f of x is ax plus b. In this example, the difference of x is 1, so continue with the sample moments by looking for the first and second moments. Mu wants the summation of values of y multiplied by h, so that is 1 times the quantity of 1 plus 1.8 plus 3.3 plus 4.5 plus 6.3, and mu 1 is then computed as 16.9. The second moment considers the summation of x times y multiplied by h, and by doing so, mu 2 is then taken as 47.1. For theoretical values of sigmas, the procedure would be similar with any example requiring best fit lines. The only things changing are the limits. In example 2, the upper limit is taken as 4.5 and the lower limit is negative 0.5. By plugging these values in the equations after integration, sigma 1 is then taken as 10a plus 5b. The second theoretical moment also uses the same equation and only the limits changing. In this case, it would be 4.5 for the upper limit and negative 0.5 for the lower limit. So by plugging them into the expanded equation, sigma 2 is equated as 30.4167a plus 10b. Equate mu with sigma, thus, the first final moment is 10a plus 5b is equal to 16.9, and the second final moment is 30.4167a plus 10b is equal to 47.1. Again, using substitution, take equation 1 and extract b. That would be 3.38 less 2a. Denote these as equation 1a. By plugging equation 1a into equation 2, a is then found out to be 1.2768. Use this value into equation 1a, making it 3.38 minus 2 of 1.2768, so b is computed as 0.8264. Thus, the equation for the best fit line for the dataset is given as f of x is equal to 1.2768x plus 0.8264.